This video is about portable generators, specifically NEC 25034 and bonding and grounding requirements for portable generators. You want to remember to always check with your local AHJ authority having jurisdiction and your local and state codes and amendments. References today are going to be from the 2023 NEC National Electric Code. When you're considering bonding and grounding of a portable generator, two terms that come up in the NEC are SDS and non-SDS. So SDS stands for separately derived system, and obviously non-SDS would be non-separately derived system. Codes associated with those can be found in 25034 of the NEC, and we're going to discuss what those terms mean. In the slide I have up now, the NEC defines separately derived system. It's an electrical power supply outlet other than a service, having no direct connection to the circuit conductors of any other electrical source other than those established by grounding and bonding conditions. Typically, with a portable generator, the only way you have a separately derived system is if the transfer switch switches the neutral, so the neutral becomes disconnected from the service neutral. And again, considering a portable generator, a non-SDS, non-separately derived system occurs when the neutral stays connected to the service neutral. So essentially this SDS or non-SDS classification only exists by how you're connecting the generator, by how you're using the generator. That's how the NEC looks at it. It's not how the generator was built or shipped or whether or not the neutral is bonded to the frame or not. It's how are you going to use the generator? How is it going to be connected? In this next slide I have up, it has some of the NEC requirements for portable generators. So under NEC 25034A, the NEC tells us that a portable generator is allowed to run cord and plug equipment without a GEC, a grounding electroconductor, if it supplies only equipment mounted on the generator or cord and plug equipment through its own receptacles, meaning the generator receptacles, and the non-current carrying metal parts of the equipment grounding terminals are bonded to the generator frame. But also in conjunction with that, NEC 44520 tells us that for 15 kW or smaller portable generators, the 125 volt 15 and 20 amp receptacles must have listed GFCI protection unless those 125 volt receptacles are interlocked and they cannot be used at the same time the 250 volt receptacle would be used. So when you switch over to the 250 volt receptacle, it locks out the 125 volt receptacles. So I've mentioned before, I'm an electrician also, and this was a small project that we did at our church. So we installed a small transfer switch and we have it connected to a portable generator when needed to power things like our sumps and some heat and lighting. I go to a small church, so this was economical for us at the time. But I thought this would also be a good opportunity for me to show you what the code requires for portable generators, and hopefully by visualizing it, making it easier for you to understand the requirements. So in the next slide I have up here, you see the generator that we installed. We installed a Westinghouse generator that shipped with a floating ground. And then in the lower left, you see the transfer switch. It was a Reliance transfer switch. It's a 6-position transfer switch, UL listed, and it works perfectly with this setup. So I'm going to explain to you how this transfer switch handles the neutral, whether it's an SDS or non-SDS system at the end, how the fault current is going to return to the source, and why this setup meets NEC and the manufacturer's requirements. And also I'm going to talk about why using this generator for cord and plug equipment would not meet the NEC requirement unless there was some alteration done to the generator. So again, with a portable generator, SDS would be the generator neutral is isolated from the utility neutral. A non-SDS is where the generator neutral remains connected to the service neutral. And typically with generators where the neutral is being switched, you're going to have a system bonding jumper to the frame. So again, the setup I have up here, the Westinghouse generator and the transfer switch, the generator has a floating neutral. And because the neutral is not switched by the transfer switch, it remains connected to the utility. This is a non-SDS setup, a non-separately derived system. And the non-separately derived is the term the NEC uses. This system is not a separately derived system. So essentially, this generator becomes part of the building's bonding and grounding system. In this next slide I have up, it gives you NEC's requirement for transfer switches. So NEC 702.5, and this is an excerpt from that code section. The equipment shall be listed, designed, and installed so as to prevent the inadvertent connection of any other sources of supply. So what the NEC is telling us is this transfer switch has to be listed and operate so that there would never be an interconnection between generator power and the utility power at the same time. So with this non-SDS setup that we have, the neutral to ground bond is staying at the service per 25024A5. The generator remains connected to that same service neutral through the cord that comes with this kit. So the cord has 2 hots, a neutral, and a ground, equipment ground in it. And when we connect that cord from the generator to the inlet, we end up getting the proper bonding and grounding through the service, through the utility service. And I'm going to show that to you as we continue on. With this particular setup, with the transfer switch that we have that does not switch the neutral, we needed a floating neutral generator in order to make this work. If you had a portable generator that actually had a neutral to frame bond, so you had the neutral and equipment ground bonded together, you would create objectionable current through the EGC, the equipment grounding conductor, and the neutral. And if you look at the slide I have up here, NEC 250.6a tells us that it's prohibited, and it is prohibited because it's a dangerous condition. You could end up with stray voltage on the frame of the generator, on normally non-current carrying conductive surfaces, any metallic objects or surfaces that are connected to that generator or whatever you're powering. So again, I'll give you a visual as we continue on how this works. So on the picture I have up on the slide now, this is the inlet that we installed for this generator. And this is where the cord from the generator is going to go. And this inlet connects to the transfer switch, which is inside the building. Then in this next slide, this is the conductor. So this is how we wired that inlet. And you can see, obviously, you have the two hots and a neutral, but also very importantly, you have the equipment grounding conductor. So we're bonding the metal on this enclosure, but also you can see the equipment grounded conductor is part of the plug assembly, and then it's also going into the building with the two hots and the neutral. Okay, next, this is the junction box for the transfer switch. So you're just seeing that we have the connection of the two hots, the neutral, which are going off to the panel, and then also, again, the equipment grounded conductor is bonding the case or bonding the metal of the transfer switch, and then that also is going off to the panel. So we're maintaining that bonding and grounding path from the inlet per the NEC requirements, and going off to our service panel. Okay, in this next slide, you see the transfer switch and then you see the panel. So all the conductors are coming into the bottom of the service panel, and then you see the hot conductors off the different breakers. But also what's happening here is the system neutral and the equipment ground is coming into this panel, and it's going to the neutral bus. And that neutral bus is bonded with a green screw in this panel. So this is one of the service disconnects, and you have a green screw bonding the case or the metal of the panel to the neutral bus, to the neutral terminal, and that's where any green or white is going to go. Any grounded conductor, any equipment grounded conductor is going to end up going to this neutral terminal or this neutral bus. So if there's a fault to any non-current carrying conductive surface, it's going to work like any other fault would work. It's going to hit the equipment grounded conductor, and it's going to be a low impedance path back to the source, back to the generator. And you're going to get a high current because everything is bonded and grounded properly back to the generator, which is going to trip the main breaker on the generator. If you had a bonded generator at the other end of this transfer switch, you'd create parallel paths. You'd have multiple paths going back to the generator, and you might not get that high current surge needed to trip the breaker. And then you would have stray voltage on other surfaces, conductive surfaces like the frame or any normally non-current carrying conductive surface that's being powered by the generator. You would have stray voltage on those surfaces. Now, just as a comparison, not for this generator that I have pictured here because this is a floating neutral setup, but if you actually had a generator with the neutral bonded to the frame and the equipment grounding conductor, the way that that fault path would work with cord and plug equipment is if you had a fault to a normally non-current carrying conductive surface, what would happen is you would have that neutral to equipment ground bond, and that would follow that path back to the source. And again, with that setup, because of that neutral to frame and ground bond, that high fault condition would cause the breaker to trip on the generator. So this generator shipped with a floating neutral. The only way this could work safely with 125 volt cord and plug equipment would be if you made some type of a modification, and that would have to be a manufacturer approved modification. They sell bonding type plugs, so you can create a neutral to case bond, but again, it would have to be something that's okayed in the manufacturer's instructions, okayed by the manufacturer. The other reason this wouldn't work, and you can see in the slide I have up here, is because again, per 445, you're required to have GFCI protection on the 125 volt receptacles, and you can see that there isn't GFCI protection on this one. So you have to figure out something with the manufacturer, and then you want to be able to protect equipment with a GFCI device. Okay, so how do you determine if it has a floating neutral? Well, it's supposed to be marked per the NEC. That's another requirement, that the generator has to be marked. It has to be obvious whether it's a bonded neutral or a floating neutral. On our generator, you see the picture I have up here. It tells you by the grounding lug that this is a floating neutral generator. Also in the picture I have up here, the blue cover is covering the stator assembly. And this is one way you can verify that you do have an actual floating neutral generator. So if you see in the next slide I have up here, I have the stator cap off, and you can see the conductors coming from the stator. And if you look, you see the neutral and the EGC, the equipment grounding conductor, where the equipment grounding conductor is bonded to the frame of the generator. And if you look at the wiring schematic of your particular generator, you'll be able to follow the conductors. But right here, if you look, there is no bond between the neutral and the equipment grounding conductor that's bonded to the frame of this generator. So that's an obvious sign that you have a floating neutral on this particular generator. What I also did on this generator, if you look at the video I have up here, is I did a continuity test just to test between the neutral and the ground lug of the generator. So the grounding lug, if you follow the schematic, is connected to the equipment grounding conductor and the frame of the generator. So in the video that I have up here, I'm testing for continuity. I'm testing for a closed loop between the equipment grounding conductor and the neutral. I had my tester in the neutral on this 240 plug, and I'm touching the ground lug, and you see that I have an open loop, so I do not have continuity. So I'm not finding continuity from the ground lug to the neutral of this generator. Okay, in the next video, you see I have my probe in the neutral of the receptacle. I have my 240 volt plug plugged in, and now I'm checking with the lug if I have continuity, and you can see that I do. So I have a closed loop here. I have continuity between the neutral and the grounding lug, and then I go over and I touch the frame. Again, I have continuity from the neutral to the frame. So grounding lug continuity, frame continuity. So I'm connected to the equipment ground, but that's happening because of the plug now. Because my plug, I have it plugged in at the generator and over here at the inlet, which is now connected to my service, which is bonded and grounded correctly. So in this next slide I have up, these are all the applicable NEC codes for portable generators. So it's something you should refer to whenever you're connecting or working with portable generators. We have the non-SDS generator grounding rules, SDS grounding rules, bonding at service only, objectionable current rules, fault current return path rules, the neutral bonding identification, the requirements for receptacles, and again, 110.3b, always follow the manufacturer requirements. You should not be making any alterations to a generator unless you're following the manufacturer requirements, and that's something the manufacturer allows. If you're interested in the exact equipment I used for this setup, I'll leave links in the description for the generator and for the transfer switch. If you want a more detailed breakdown, you can go to my site, buildingcodegeek.com, where I break everything down in more detail. I hope this video helps you understand bonding and grounding requirements for portable generators a little bit better. If you liked the video, remember to give me a thumbs up and subscribe, and thanks for watching.